The topic this week is logistic regression. We've talked already about all the probability theory stuff, statistics, causality, and we've started bringing it all together with these regression estimators. We talked about linear regression at length. For the past 3 weeks, we're going to now talk about logistic regression. It's really not that different. So we're going to be able to cover everything here basically in just one week. And we're going to see it's really just a redux of all the stuff that we talked about for linear regression. So hopefully the concepts seem pretty familiar to you. Okay, so regression, what is it? It's just using data to guess a conditional mean function. So here we have the joint density of variables x and y. And what we're interested in here is the conditional mean of y given that x takes a particular value. And of course, we know that we're interested in this because it might help us describe the general relationship between these two variables, x and y, in a purely descriptive sense. It might help us predict the value of y given that we observe x, so know what's going to happen in the future with some amount of confidence. And also because we can construct plug-in estimators that, under certain assumptions, give us an idea of what the causal effect of one variable on another might be if we were to intervene. So here's a setup where we're doing regression, but the outcome variable y is binary. So in this picture, I was drawing y as a continuous random variable, so it has some kind of distribution, like let's say between 0 and 10 or something, right? So values like for a particular value of x, like here, for this particular value of x, you can see y is very likely to be kind of around here. Right, that's the conditional distribution of y given x. However, this setup is the case where y is continuous. So we could also have a case where y is binary. So if y is binary, it only takes the values 0 and 1, right? So let's say for this value of x here, the distribution of y is, if we were kind of looking at it sideways, is just going to be a probability mass function. So it's going to have 0 mass for anywhere in here, and then here it might have a particular value, and then here it might have another particular value. Okay, so that's the conditional probability function at this value. At this value down here, it might be the other way. So here, the 0 value might be very likely, and then over here, it looks like the 1 value is very unlikely. So you can see this is a discrete density function instead of a continuous density function. Nonetheless, we can still have a conditional mean, right? So at this value, for example, here, right? You see it's much more likely that y is 1 than y is 0. So perhaps the conditional expectation of y, the probability that y equals 1, in this case, it's the same thing as this conditional expectation, is somewhere around 0.9. Whereas down here, the probability that for this value of x, the probability that y takes the value 1 is very low, somewhere around 10% or 0.1, something like that. And so for this particular distribution, joint distribution of x and y, it appears that that this conditional expectation, which again is just the same as the very binary outcome, this is the same as the probability that y equals 1. Given x equals little x. So since this is a probability, we know that it's bounded between 0 and 1. Obviously, this conditional expectation, since it's a probability, can't be a value greater than 1, and it can't be a value greater than 0. That wouldn't make any sense at all. So why is that an issue for, let's say we wanted to estimate what this relationship is, this conditional expectation function is, using linear regression? Is it a problem that these things are bounded? It sort of is, because if you run a linear regression, and this is actually a thing that I actually did. So here, this density is actually like a very large population data set that I generated. And then here, this is actually the result of running linear regression on these data. And this is the fit that I get. And you can see up here in this region and down here in this region, we've actually have conditional expectations, which is predicted probabilities that are greater than 1 and less than 0, which makes no sense. So basically, my linear regression would be saying, for people whose values of x are, let's say less than 0.1, the probability of them getting the outcome is negative 5%, which is nonsense, obviously. So the problem is that the linear regression model is maybe not the best. The class of functions that we're using doesn't make sense in this setting. It doesn't make sense to search over all linear functions because there are some linear functions which do not respect these bounds. And so that's one of the motivations for logistic regression. And logistic regression is just another way of guessing a conditional mean function. It does some things a little bit differently than linear regression. So if you recall from linear regression, the big picture idea was first we have to pick some set of candidate functions. If we're trying to guess a function, we have to pick some set of candidates. Then we have to pick a way to grade how well a particular candidate fits the data. And then we develop an algorithm that will search all of these candidates to find the one that has the best fit according to this grade. So we're going to do the exact same thing for logistic regression. We're just going to make slightly different choices. So first off, let's pick some candidate functions. So with linear regression, we are getting some lines, but we don't want straight lines anymore because we know that the lines are not going to obey these bounds of staying between 0 and 1. So what we're going to do to solve this problem is we're going to say, well, okay, let's still make a line. Okay, so there's some linear relationship with x. But now the problem is that that thing goes outside of 0 and 1. So let's just squish it down. Let's just pick a function that takes any real valued input and squishes it down between 0 and 1. And let's just wrap the output of that line in that function so that it gets squished down. All right. And the function that we're going to use for that is this logistic function, which we've seen before, and we use for generating data. And so effectively, we still have a class of functions that's parameterized by an intercept and a slope. It's just that now these are not really, they don't look like intercepts and slopes anymore because this line is being wrapped up in this other function. So for a quick reminder, that logistic function is 1 over 1 plus e to the minus its input. And in this case, the input is the output of the linear function. So how does this thing behave in terms of this slope beta and the intercept beta 0? Because obviously this is no longer a line, right? And so all of these are, this intercept is not really, what I'm calling the intercept is not really the intercept, and what I'm calling the slope is not really the slope, because these things obviously have slopes that change as x changes. So what's going on here? So first things first, let's just look at what I'm calling b here. So this is the slope parameter on x. So you can see when b is negative, the relationship between y and x, small values of x give more 1s, large values of x give more 0s. So that means there's an inverse relationship between x and the probability of the outcome. So for example, if this were age, and this were probability of a particular outcome, a negative coefficient would be saying like older people are less at risk. Okay. Compare that here to the case where we have a positive coefficient. The positive slope says that the older you are, the higher at risk you are. And what about the magnitude, the overall magnitude of this thing? So you can see as we go from -5 to -1, we have a less sharp drop off. That's what's happening here. So if you compare the brightest pink curve here to this pink curve, if we have this very high coefficient, it means there's a very stark cutoff at some point where the risk goes from nearly 0 to nearly 1 very, very, very quickly. Okay. Whereas if the slope is more moderate, then the risk profile changes more moderately with this predictor variable. When we have a slope of 0, it's flat. Okay, so you get the same risk basically for everyone. And with the smaller but positive slope, then we have a moderate increase in risk as the predictor varies. So that's everything we can say about the slope parameter. And now what about this intercept parameter? Well, the intercept basically just changes what the baseline risk is. And in these curves, what that amounts to is if you have a negative coefficient, a large value of the intercept shifts the curve to the right. So relative to let's compare the gray curve and this pink curve. So the gray curve, the intercept is -5, and the pink one, the intercept is 5. So the pink one, since it's shifted to the right, the people who are in this band of values, let's say like between 0 and 2, all have very high risk, whereas for this curve, they all have very low risk. So the intercept says, basically, if you have a large negative value, there's more people who are at low risk. And if you have a positive value, there's more people who are at high risk. It's very easy to see that in these plots, right? So here, in the gray curve, most of the people would be, let's say it were a uniform distribution over X, then most of the people would be falling in this region, and very few would be up here. Whereas if we had the pink curve, you'd have a lot more high-risk people and a lot fewer low-risk people. And it's very, very easy to see in this case, where there's no slope, there's no change in the risk. If you have a negative coefficient, everyone's at low risk, intercept. If you have a large intercept, everyone is at high risk. So it just modifies the baseline level of risk for a person. And then the covariate, where you are on the covariate changes how much more risk you have than this kind of baseline level. That's basically the idea. All right, so logistic regression, nice. So we have some candidate set of functions, right? They're parameterized by the slope and the intercept, so we can get a lot of different shapes, a lot of these different S shapes. That is not every possible shape, okay? So there's still many, just like linear functions don't capture parabolas and don't capture many different kinds of conditional mean relationships like this one, right? We could not fit this with the main terms linear regression very well. Same thing with logistic regression. It doesn't fit all possible relationships between y and x, right? What the risk profile is. So here's a case where, let's say you had a population data set that looks something like this. This is a very small, population. But in this case, it looks like, you have high risk for people in here and low risk for people on the outside. And so maybe the relationship would be something like that. You're not going to fit that with a logistic regression because there's no way to fiddle these numbers to get a curve that goes up in the middle and then back down. You can only have these S shapes that either go up or they go down or they're flat. So there's plenty of functions that are just not well modeled by logistic regression. But what's nice about it is that we have boiled it down basically to a parametric problem, just like linear regression, where we've taken a very hard problem, which is we have all these functions that we could possibly have, and we've boiled it down and we said, okay, let's just consider linear functions. And what that buys us is that we can describe all linear functions of a single variable with just two numbers, the slope and the intercept. So logistic regression, same idea. We've boiled down all possible functions to just, these kind of S curves. And yes, that's a limitation. But what that buys us is that we can describe every one of these S curves with just these two numbers, this slope and this intercept. So we can draw a point here on the kind of a beta 0 beta plane and say, okay, this particular F corresponds to the S shape that has this slope and this intercept. So that's our class of functions that we're going to be working with for logistic regression. Now this next step is we need to pick a way to grade how well any given candidate fits the data. So if you recall from linear regression, the idea is that we have some data set and we draw our curves and you say, okay, how good of a fit is this? So maybe this one doesn't look so good because over here we're saying that for people in this region, they should be about half. The risk should be about 1/2. But I'm looking at what the data, and I have these two people and kind of nobody down here. So everyone's really getting the outcome. So actually, my risk should be really high about here for this value of x. Similarly, for this one, in this region, the risk should be maybe about 1/2 because I have kind of 2 and 2. But here, this one is predicting a much higher risk already. And so maybe this middle one is about what I want. So how do I quantify that? How do I make that more concrete? We saw that for linear regression, what we did was that we quantified it with squared error. So we took our predicted conditional mean, and which here I'm calling p hat because it's a prediction of a conditional probability, and then we calculated the residual. So here's the value that I think I should be getting. Here's the value that I actually get. It's a 1 or a 0 in this case. Let's measure this residual. let's square it, and let's find the curve that has the smallest sum of residuals across all of the data. And that's okay. There's actually really nothing that wrong with that fundamentally. We could just use mean squared error. But there's some kind of practical considerations that make that not the best for this class of functions that we're using. So for one, it's kind of interesting that if you think of the residual or as like a cost, right? Like how much do I have to pay for making an error of this magnitude? Let's say that you were predicting here, my prediction was 0. So I predicted 0 risk, but then I observed actually that somebody had the outcome. It seems like that's a pretty big error, right? If I'm predicting nobody should have it and somebody should have it, that's just qualitatively kind of like the worst. Yet I'm still, if I'm using the squared error, I have 1 minus 0 squared is 1. So I'm kind of paying $1 for that error. Whereas let's say I predict probability of 1/2 and I see somebody with the outcome at that probability, I'm paying 50 cents. 50 cents squared, so 25 cents for that error. So why should I pay only 4 times as much for an error that is, basically an impossibility, right? I said something could not happen, and then it literally could not happen. It's impossible, and then it happened. That seems like a pretty big error to make. So I kind of don't like that. And so one solution that people use, and this is what is done for logistic regression, is that they use a different loss function. And the loss function is called many things. I'm going to call it cross entropy because that's kind of what it's started being called in the deep learning literature. But it's also this. It's called multinomial log loss. It's called binomial deviance. But it's all the exact same thing. And this is the formula here, which you can totally ignore for the second. I'm just showing you the shape of it, right? So if this is the probability of the outcome, and this is my, let's say for y, this is for y equals 1. So this is the loss function when y equals 1 as we vary p hat. So you see what's happening here is that if we predict 1, when y equals 1, the loss is 0. So the mean squared error and the this kind of log loss agree. But as we increase the predicted probability of the outcome, or we decrease it, sorry, which we know is the wrong thing to do because here y really is 1, we start paying more and more and more. And in fact, as we get close to 0, this thing shoots up to infinity. Here it looks like it actually hits it, but that's an artifact of the way of the plotting. It actually asymptotes up. So what that means is that if I make this error where I say something is impossible and then it actually happens, I'm paying infinity dollars, right? So I'm really, really punishing that. So it shouldn't happen, right? It should never get a model that has that happen. Okay, so the formula now looks a little bit weird, but it's actually a little more sensible when you write it like this. So it's when y equals 0, you take the minus log of the predicted probability that y equals 0. And when y equals 1, you take the minus log of the predicted probability that y equals 1. So a little bit more sensible to at least remember it like that. And this is 1 minus this, right? So you can just predict the probability of the outcome and then take 1 minus that and plug that in there. So another even simpler way to write it is that it's the minus log of p hat of big Y, the observed outcome, equals whatever little value that you're evaluating against. This is also, not something you have to know, but for those who are curious, this and know something about maximum likelihood, this corresponds to the negative log likelihood for this model, and so in a sense, this is the right thing to be doing, the same way that the mean squared error is kind of the right thing to be doing in the continuous sense. If you're assuming normal errors, but well, we don't have to talk about that. Okay, so that's the loss, and that kind of gives us a residual. So it's not a residual like this because it's not really just this distance squared. It doesn't have to do with that distance, but it does have to do with what the predicted probability is here and what the value of y is. We just have a penalty that increases in a different way, right? So it increases much more quickly than this. It increases like this. So for each residual, we have like a penalty associated with it. And then what we're going to do is just add them all up for all the data points. And that is going to be our overall loss, our judge of how good a particular candidate function is. Okay, so the last step is to develop an algorithm to search the candidates to get the best fit. And here we just do gradient descent, same as linear regression. So again, the intuitive idea is that you start with a guess for your slope and a guess for your intercept, and you look around. You consider modifying, tweaking your slope and intercept by a little bit in many different ways, and then you see what kind of tweak gives me the best decrease in loss, and then you accept that and you move there, and then you repeat that process. And this can be, in fact, automated. You don't have to even do that search. You can just use calculus to figure out which is the direction you need to move, and eventually that will give you the lowest loss. So you're just minimizing the loss as a function of these parameters, beta 0 and beta, and you go down. So this is actually another reason that cross entropy is nice, because if you have a binary outcome, if you actually set this up and look at the mean squared error as a function of beta 0 and beta, and you were to plot this. So here I'm just looking at like this is like my top down plot, and then this is my, from same picture but from the side. If you look at mean squared error, it's actually not going to be a very nice function. There's going to be these little dips and valleys and crevices. So for example, around here, where you might get stuck if you're just trying to go downhill. So you could imagine there's like a little lake, a little pool of water here that is not waterfalling down to this pool of water. And that's not great. Whereas if you use cross entropy, actually, you're always guaranteed in this setup with the logistic regression to have a single unique minimum that you will find. So that's another reason that people prefer the cross entropy loss to mean squared error in this setup, is because you get this what's called convexity of the loss function. Okay, that is all of regression methods, right? We pick a candidate set of functions, pick a way to grade, develop an algorithm to search. So for logistic regression, the choices that we made are linear functions, but we just wrap them in this logistic wrapper. For the loss function, instead of mean squared error, we chose cross entropy for a couple of practical reasons. And then for the search algorithm, we just use gradient descent, same as linear regression. So really the main difference is here, right? So it's the fact that we wrap these linear functions in this logistic, so we're getting a different candidate set of functions. That's it. We're still going after a conditional mean. We just changed the set of candidate functions. That's the main thing. So all of this, if you want to do it manually, of course you don't have to. We will see how to do this in R in a second. But it's not that crazy. You can ask ChatGPT and it'll implement it from scratch, right? In R. So if you're curious about that, you can just have a look.